Next, question number 8. Yeah. This one, much harder one. Much harder. N factorial. How can you handle n factorial, right? So this is the most difficult one in this section. Yeah. N factorial. Yeah. Here we say n factorial belongs to little of this special function, n to the nth special exponential function. Very big, very big. N factorial, when we compare these two functions, little o, the limit of n factorial over n to the nth, the limit should be 0, but the question here, the hard part of the question, limit. N factorial, how can you take the limit of the function like this? Even you replace by continuous variable, for continuous variable, what's the meaning of x factorial? Right? The definition is not that clear. Yeah. Although there is a definition. Yeah. Later we will see there is some generalization of n factorial. Yeah. But we won't go that way. Even you have the definition x factorial, how to take the derivative. Nobody can tell you what is the derivative of that. So that's why the derivative way is extremely hard. We cannot use the L'Hopital's rule here. So when you see n factorial, don't try to use the L'Hopital's rule. No way you can do it. Nobody can do it. Yeah. So you have to choose a different way when you see n factorial. Okay? Here we use another formula from calculus 2. There is another famous formula related to n factorial. That is the Stirling's formula. Stirling's formula give us estimate for n factorial. Okay. So what is that estimate? Yeah. Here, n factorial approximately equal to square root of 2 times pi, strange, pi times n, then outside parenthesis, n over e, natural log base, e, all right? N over e, the whole thing raised to nth power. That's the Stirling formula, right? Yeah, we need to use this estimate, Stirling formula. Otherwise, we cannot handle n factorial. Yeah. But when you use the Stirling formula, yeah, here, another thing is not very friendly for us. Look at this approximation sign. Approximately equal, we have problem with that. Because when we want to do some serious math work, that approximate does not provide us precise information. So we have problem with that. Approximately equal, we have that. So we have to change a different version of Stirling formula. Stirling formula has another version we need to use. That is the inequality version, not the approximation version. Inequality, yeah, we need that. We need upper bound, lower bound, inequality version. Yeah. So let us take the inequality version of the Stirling formula. That is the inequality version of Stirling. Lower bound, root of 2 pi n, yeah, the same as that, okay, the lower bound. But upper bound, yeah, that root of 2 pi, we change that to constant e. Natural log base, constant e. See, 2 pi root lower bound constant, upper bound constant just e. Remaining the same. That's more friendly. This inequality formula, Stirling formula, more friendly for us to do the calculation here. Yeah. All right. Yeah, so now we can do the remaining calculation. Work starting from this inequality. Okay? This inequality. All right. Next, the work let us do, So start from there. Let us take the ratio of the f function and the g function. F of n factorial, g of n to the n, ratio of the function. If you look at that in this formula, you do the division, each side divided by n to the n. After simplification, you have this inequality. That inequality. All right. Then, next step, we know we need n goes to infinity, and we want to see the limit when n goes to infinity. Yeah. Let's take the limit when n goes to infinity. All right. But when you do that, make sure the little things, be careful, the little things, the original inequality strictly less than, but when you take the limit, change the strict less than to less and equal, because the limit will include the equal case. Original formula, strictly less than or strictly greater than, non-equal, unequal, right? But when you go to the limit version, make sure you include the equal case. Otherwise, you will lose a special case, equal case. Yeah. So that's typically we do in calculus. Now let us move to the next step. All right. Look at the limit of the leftmost term. Look at the limit of the rightmost term. Can we see the limit immediately? Look at the numerator function, denominator function. Numerator function, denominator. What is that? The numerator function is a power function, right? Exponent 1/2. Denominator function is an exponential function with the base greater than 1. What is the ratio of that? We did, right, before. Think about that. Limit is 0. When you compare a power function and an exponential function grows much faster than power function. So the limit equals 0. Similarly here, the limit goes to 0. The power function over exponential function, the limit goes to 0. Look at the two ends, limit of two ends. Both ends, the limit go to 0. Then the limit in the middle can only go to 0. The limit in the middle can only go to 0. Here we use the previous example. N to the d, that d is 1/2. Exponential function, a equals e, little o, that means limit equal to 0. Here, these two limits, we just use that result. Okay, all right. Then after that, both sides goes to 0, then there is a theorem called a squeeze theorem or sandwich theorem. Some people call sandwich theorem. Some people call squeeze theorem. You squeeze the limit in the middle from both sides. Both 0, you do the squeeze, the middle part can only be 0 by the squeeze theorem. Or sandwich, the sandwich in the middle, the meat in the middle, must be 0. Okay, must be 0. So that is the answer. You see? You see? This 0, limit 0, tell us little o notation. Okay, all right. So you can see this is the hardest example in this class. Hardest example. And from this example, you can see we need a lot of pieces of knowledge, many pieces. Okay? Stirring formula, squeeze theorem, L'Hopital's, here we do not apply L'Hopital's rule. Yeah. Yeah. All right. Yeah.